Hey guys, just to let you know, this lesson is in collaboration with Flip Academy, a free online platform for all of your GCSE, A-level, IB and CBSE revision, out now on web at www.flip.academy, and also as an app for Apple, iOS and Android. It really is better than all the other GCSE platforms out there. It covers all the topics in great depth and has an app that you can download your courses on and use offline. Hello and welcome back to Flip Academy. Today we're going to be looking at numerical solutions of equations. This is going to contain a bunch of graph sketching, it's going to contain a bunch of algebra as well, and that's going to be pretty exciting. So with numerical solutions of equations, this first spec point really does sum up the entire topic. Okay, so we need to be able to locate approximately a root of an equation, and if you remember, the word root just means solution for our purposes, okay? So we just need to be able to locate a solution of an equation by either a graph or searching for a sign change. So with a graph, as hopefully you may know, if you were to sketch a graph, so let's make it quite easy. Let's just make this some kind of quadratic, okay? And you were looking for a solution to when that quadratic equals 0, okay? So it could be any quadratic you like. Maybe we can call it something like x squared minus 2x minus 3, right? Something like that. What you can do is you can actually look at the graph and try and spot when it equals 0. So when a equation or a function equals 0, it crosses or intercepts the x-axis. So those 2 points here are going to be our points of intersection, so they're going to be our solutions to the equation when that equals 0. Okay? Technically speaking, you could also have it equal to some lines. So let's say it could be equal to 2, and you'd look for when it intersects the line y equals 2. And once again, where they cross are your solutions. So you can literally just read them off of the graph if you were to plot it, which is a very useful skill if any of you plan on going to university and doing things like maths or physics or something along those lines, because you're going to be plotting graphs and spotting points of intersection quite a bit. You probably do it using a computer though, but it's good for you to know exactly how to do it by hand. Now there is one other way, and this is specific to when it equals 0 only. If you have a look at this function, right, and we're just going to look at, again, when it equals 0, so we'll get rid of the other stuff quickly. Redraw our curve. Before it crosses here, can you see that this would be a positive value, and afterwards it goes to a negative value? Interesting, right? And here it goes from a negative to a positive. Well, this is because if you're looking for when a root or a solution is equal to 0, there's going to be a change of sign. So what I could do is, let's say this value here was 1, and this value here was 2. If I sub in x equals 1 and x equals 2, and I notice that there's a change in the sign, either from negative to positive or positive to negative, then I can say that this implies that there is an existence of a root between 1 and 2. And from there you can use something like iteration in order to find what the exact value is. Okay, so that's basically the notes on this. Okay, we're going to go through some questions though to make this seem a lot more, make a bit more sense. So for part 1 it says, by sketching each of the graphs y equals cosec x and y is equal to x pi minus x for 0 to pi, show that the equation cosec x equals x pi minus x has exactly 2 real roots in the interval. Okay, so let's draw out these two graphs. So that'd be our x-axis, that'd be our y, and again it's just a sketch, you don't need to make it super exact. So with the cosec graph, it kind of looks like the tan graph in the sense it has these repeating asymptotes. One is at pi over 2 and the other one is at pi. Okay, and for the cosec graph, it starts at 1 because again it's 1 over the sine graph. So it starts at 1 and it shoots off towards infinity here because that's when it's going to equal, it's going to be 1 over 0. And after that it's going to do the same thing but down. My sketch isn't exactly perfect, but again this would be negative 1. Okay, it doesn't need to be perfect, you just need the general shape, and there's a very specific reason. Now for the x pi minus x graph, if you were to kind of draw that out or expand it quickly, you would have minus x squared plus pi x. So this is just a quadratic, but it's a negative quadratic, which means it's going to be a big sad face, okay, or an N shape. And where does it cross? Well, if we look at the actual solutions here, it crosses at x equals 0 and x equals pi. So that is this point here and this point here. And then you're going to have a big U shape. Okay, so you're going to have a big U shape like that. Cool. And it says show that it has exactly 2 real roots. Well, we're looking for when these graphs are equal. Now, if you're looking for when 2 graphs are equal to each other, that means it's when they intersect. Okay, so 2 real roots in this instance is when the 2 graphs, so when the 2 graphs intersect. Okay, so that is here and here. So they intersect twice. Intersect twice, therefore 2 real roots. Nice and easy, okay? 3 marks, so you get a mark for each of the kind of drawings being appropriate. So the rough right shape and having the correct kind of asymptotes and things like that. And then you get the last mark for actually making the logical deduction that since they cross twice, there must be 2 roots. If they cross 3 times, there's 3 roots. If they don't cross, then there's no roots, and so on. And this is very similar. So by sketching a suitable pair of graphs, show that the equation 5e to the minus x equal to square root x. So if we have a look at what this will look like, so I'm going to draw it relatively shallow. So 5e to the minus x is an exponential decay. So it starts from plus infinity and it goes along this, and it will go on forever, and this would obviously be 1. And the square root x graph actually starts down here, and actually this would be 5 because it's times by 5. This would be something that looks like that. Okay, and that starts at 0 because the square root of 0 would be 0. Perfect. So if you notice, there's only one time that they'll ever cross, and they'll never ever cross again. So again, we're just going to write one point of intersection, point of intersection, means 1 root. Okay, so that should be nice and easy. Again, this relies on you knowing the various different shapes for different graphs. One thing you can do is kind of try and use your logic and your deductive skills to try and work it out. You can also use a calculator to just kind of sub in various values to see which ones work for you. Okay, so if you had a calculator, you could just literally plug in values and see how it behaves over time. Some of your calculators, depending on which one you have, will also be able to plot a table for you, so you can kind of see what the values are doing with time. Okay. Next thing. So understand the idea of and use the notation for a sequence of approximations which converges to a root of an equation. Okay, it's pretty fancy talk. So what they're trying to say here is an iterative formula to find solutions, and they do have this general form: xn plus 1 equals fxn. So you might have something like, let's make it relatively light. So you might have n plus 1 equals xn squared over 3 or something like that, right? And they give you, sometimes they give you a starting value of, let's say, 1. Sometimes you have to find or figure out or think about which value it should be and sub that in. But the idea is that as you continuously use this formula, so you start with x not equals 1, so 1 squared over 3, that's 1 over 3. Then you put it again, so 1 over 3 squared, so that's 1 over 9 divided by 3, 1 over 27, and so on. It should converge to a specific value. In my instance, it's going to converge to 0, so that would be the solution to whatever equation I've created here. But again, I did just make that up on the spot. So understand how a given simple iterative formula of the form xn plus 1 is equal to fxn relates to the equation being solved, and use a given iteration or an iteration based on a given rearrangement of an equation to determine a root to a prescribed degree of accuracy. That's a lot of fancy talk. Essentially, you're going to be using these equations to find a solution to a certain number of decimal places. So the problem with these kind of numerical solutions, and this does happen a lot in real life too, is that there are equations too complicated for us to solve. Right? So you have things like the 3-body problem, for instance. So what we do instead is we get a numerical answer, right? So we get a computer to do iteration hundreds of times, and it will give us a value to, let's say, 10 decimal places. And we say, you know what, beyond that, I don't care. 10 decimal places, that's a billionth of a single unit of accuracy. That's good enough for me. Okay? And normally it is good enough. But that's the idea, is that these are always going to be approximations. Okay? So let's have a look at this. Use the iterative formula an plus 1 equals 2ln 16 minus an over 6 with a1 equals 2 to find the value of a correct to 3 decimal places. Give the result each iteration to 5 dp. Okay, so what are we going to do? Well, let's have a look-see. What I would do, and this is pretty specific, is I just get a1, so I press 2 equals. And then I'm going to rewrite the exact same formula. However, instead of an, I'm going to press the ans button. And the reason for this is the ans button stores whatever your last answer was. So in my case, it's going to be 2. But when I press equals, it's going to take whatever that answer is and sub it in for me. So essentially, I can do iteration by just continuously hammering the equal sign over and over and over and over again. Okay. So we do need to give each iteration to 5 dp, which is it's a bit frustrating, but in real life you would just press equals until, and I'll show you what. So we only want it correct to 3 decimal places. So what we're going to do is we're going to wait for the first value, or the first 2 values, that round to the same number to 3 decimal places. Okay? So I'll show you what that means. So we're going to press equals. So A2 is 1.694595 blah blah. So I'm going to round that to 5 dp as it tells me to. So A2 is equal to 1.694. Then it would be 60. Right? So to 3 decimal places, this rounds to 1.695. If my next value rounds to 1.695, then I'm done. And the reason for that is the result converges. So you'll notice as I keep hammering the equal sign, it's going to change less and less. So again, we're going to do this one now. So we have 1.7377, and then instead of 5, it's going to be 6 for 5 decimal places. So they don't round to the same number, and you're going to just keep doing this, okay? Now, in an exam, you can do this a lot faster than I'm doing it, but I'm trying to explain it. So press equals again, 1.7. So you see, have you noticed it hasn't changed as much? So it changes by a lot really quickly, and then it slows down over time. So let's go again. 1.73173. So if I look to 3 decimal places, they're both the same to 2 decimal places, but not to 3, so we have to keep going. So A5 equals, and it should change by even less, 1.7325 blah blah blah. So and I'd actually recommend trying to write it out relatively neatly, which I'm not sure if I'm succeeding in doing at the moment, because what I'm doing is I'm trying to line up the decimal places so I can see if they're changing or not. So if I look here, I can literally just read it off. So if you notice, these 2 values are the same to 3 dp. Now if I were to press equals again, and I would recommend doing one more just to be sure, I get 1.732 again, right? And if I press it again, do you notice that fewer and fewer decimal places are changing? So my answer for A is equal to 1.732 to 3 decimal places, right? That would be what you would do as soon as it stops changing. So in this case, we would need to find what A6 is, because that was... So that would be 733. My apologies. Because A6 was 1.732, it was 6 something, I think. Right? So these 2 things here have the same value to 3 decimal places. So that's the one we're going to use. These 2 are very similar, but they're slightly different. So this is 731, this is B733, but the next one was 733, okay? So that might be a better way of doing it. So if we just get rid of that. Okay, so hopefully that makes sense. And that's basically what iteration is for this. So if you notice, we've done this first part before. Right, by sketching a suitable pair of graphs. We've already done that. Okay. But what we're going to do is, now we need to actually find the set of values. So show that if a sequence of values is given by the iterative formula converges, then it converges to the root of the equation. So how would you do something like this? Well, what I would do is I would take this equation here and try and get the original expression, because that shows that what they've done is taken this equation and rearranged it into this equation. Now, sometimes, or usually to be honest, part 2 is actually show that the iterative formula is this, in which case you would go from this equation to this one. In this case, I've given you something slightly different, which is why I wanted to put it in the video. So we're going to go from this back to this. So let's write it out. We have x equals a half ln 25 over x. So instead of the n's and the n plus 1s, I'm just leaving it as x. Okay. And now we're going to try and rearrange to give me the formula shown above. Now, if you remember your power rules for logarithms, if you have a power here, you can just bring it to the front. So we can actually go backwards and do the same. So this is the same thing as having x equals. So I'm going to do this in very kind of concise steps. So you would be able to do this a lot faster. You don't have to do every step I'm doing. I'm doing this more for demonstration purposes, just to make sure that everyone's completely fine with this. So if you have something to the power of a half, that means you're square rooting. So you have x is equal to ln, and then you'd have... Okay. So I'm going to just do this in very precise steps. Again, you could do this a lot faster. 5 over square root x. So a question that you might have is, why are we ignoring the negative value of the square root? Right? Because technically it would be plus minus 5. Remember, you cannot square root a negative number. So if I have a negative in there, bad things will happen to me. So I'm not going to do that. Okay. For the next step, what we're going to do is we're going to exponentiate both sides. Actually, before that, what we'll do is we'll bring the power up. So what we can do, we can make this 5 square root x to the minus 1. Okay? So actually, this 5 would be on the bottom as well. So all I'm doing is I'm flipping the fraction here. The reason for that is if I look back at the answer, right, the 5 is actually on top, if that makes sense. So I need to times both sides by 5 at some point. The only way for me to do that is if the 5 is on the bottom. So that was my logic there. That's why I quickly changed it. Using the power rule again, I'm just going to make that negative ln root x over 5. And what we're going to do is divide both sides by minus 1. So we're going to move the minus over to the other side. ln x over 5. We're going to exponentiate both sides. So we have e to the minus x. Again, the reason why I need to do that is because if I look at the answer, there's an e to the minus x equals square root x over 5. And last but not least, we're going to times both sides by 5 to get 5 e to the minus x equals root x. So because we can change this iterative formula back into the original equation, it must be a converging sequence for solutions for this question. Then for part 3, we'll do it back up here so we actually can see the iterative formula. It says x1 equals 1, and we're going to do the exact same thing. So we're going to say 1 equals, and then we're going to type in this exact formula. So I leave it in the exact same form too, just to make sure there's absolutely no way I can make a mistake. Answer, whoops. He says as he makes a mistake. And we're just going to keep pressing equals, right? So we need to do it to 2 decimal places, so slightly less painful than it was before. x1 is equal to 1, x2 is equal to 1 point. Each result to 4 decimal places. Okay, so 6094. x3, we're going to press equals again. 1 point, that changes by a lot, so I'm not even going to consider that. And then that'd be 5. Again, just pause the video if you want to read the numbers to make sure I'm not making a silly mistake. And making sure that you get the same answers as well. Okay, yeah, we're still nowhere near being the same. Getting closer though. There we are. Okay, now we're cooking with gas. 1.4231. And again, I am attempting to keep them roughly in line with each other just to make it nicer. And again, we want to make sure it rounds to the same number in 2 decimal places. So right now it doesn't. 1.4330. Okay, we're getting really close now. So 423. Yeah, so we've got 4.2 and then 4.3. Interesting, okay. So it looks like we have got our solution. So if you notice, both of these round to 1.43 to 2 dp. So does it say calculate the root? So the root equals 1.43 to 2 dp. And if we were to keep pressing equals, you should notice that still 4.3, 4.3, 4.3, and so on, right? Because it only gets more precise. And then eventually your calculator will just stop because it doesn't go any more precise than that. Perfect. Not too bad for 3 marks. It is kind of a free 3 marks as long as you don't make like a silly error. But, okay. Now this, if you notice, you know, if you have a shockingly good memory, this is the exact question we did back up here. It's the very first question, okay? So what we're going to do with this is I'm actually going to keep an eye on this. So we could even move the question up to be there. But part 3, if you remember rightly, there were 2 solutions, right? There were, because it intersects twice. And it says use the iterative formula to find alpha correct to 2 decimal places. Give the result of each iteration to 4 decimal places. Okay, so if you notice, I need to pick a value myself. Okay, so I don't know what my kind of x0 or x1 is, right? However, if I go back to the original graph, alpha, if you look here, is the smaller value of beta. It's smaller than beta, right? So it's the smaller of the 2 solutions. So alpha is going to be this one here, and beta is going to be this one here. So, okay. Pi over 2 is this value over here. And if I look at my sketch, it should be under half of pi over 2. So pi over 2 is half of 3.14, so it's going to be under 1.5, right? And it looks like it's really, really close to the beginning, right? Which does make a bit of sense because they do increase quite rapidly. So if I just pick 0.1 as an example, let's see if we can do that. So because we want to pick a number that is much smaller. So just to go through my logic one more time, I know that it's going to be less than pi over 2, right? Because it's on the left-hand side. Bear in mind, if I pick a value bigger than pi over 2, I'm going to just get something that goes off to infinity because it's nowhere near the actual solution. Now, the good thing is even if you pick something like 0.5 or 1, it would still converge to alpha. So that's a handy thing. So why did I pick 0.1? Well, I was being cautious, right? If I know that roughly here is 1.5, roughly, then I want to make sure that I'm a lot less than 1.5 so it doesn't go up to beta and then I think beta is alpha, right? So I'm just going to pick something that's really quite close to 0. That's where I got the idea of picking 0.1 from. Okay, so this formula is a bit more painful to sub in, but you know, keep in mind it is just substitution. It's not, you know, the end of the world. And it says to do it to 2 decimal places. So 0.1 equals, and then we're just going to have a fraction. Now there is also another thing, which you know, I've seen some people get wrong with this question. We need to be in radians mode, okay? Because the x-axis and also the range is in radians. However, I've seen a lot of people just kind of jump straight into it and leave it in degrees. The problem is you will still get an answer. It's just they, you know, won't be the right one. So, kind of pointless. Equals, we get 3.19. And so, oops, my bad. I need to actually change over to the right value. So, I'm just going to enter it in one more time. answer squared sine answer over pi sine answer. Okay. And the values I'm getting for subbing those in are 0.7435. Again, we're just doing to 4 decimal places. 6462 is equals again 0.6615. 0.6574. Ah, good. If you notice, both of these round to 0.66 to 2 dp. So alpha is going to equal 0.66 to 2 dp. Perfect. And now it says deduce the value of beta. So what your kind of natural inclination might be is to just sub it back into this formula. There is a weakness of iterative formulas, is they'll only ever give you one solution, okay, which sucks a bit, okay? So what you need to do instead is you need to actually use the fact that this is sine, right? So with sine, in order to find out the other trig values, all you do, again, you can remember the cast diagram if you'd like. So, or if you use the graphs, you can use the graphs. I personally use the cast diagram. So we have one value in all, which is the 0.66. But then you'll also have, because it's a positive value, right? We know it's positive because it's in the positive quadrant, so it's in the top. So to work out that value, you just do beta equals pi minus that, because again, remember this is pi over 2. That's pi. Okay. So pi minus 0.66, which if you put into a calculator, you should get 2.48. Perfect. How do I know it's sine? Well, simple, cosec just equals 1 over sine. Right, so hopefully that makes a bit more sense with regards to that. And that kind of brings us to the end of the iteration kind of topic. The key thing is that if you got through this video and you're happy, that's really great. But what you need to do is go onto Flip Academy, go through some questions, and sketch as many graphs as possible, and just make sure that you're okay with rearranging algebra. Okay, if not, you can find videos doing those on the website. But until then, I shall see you in the next one.